Okay, thank you everyone. So I'm going to be talking a bit today about our white paper, contextually defined postural markers, reveal who's in charge, evidence from small teams collected with wearable sensors. This work emerged out of some of the research we've been doing, in particular with the sociometric badges developed by MIT Media Lab, which I'll introduce briefly in a moment, and also some very simple experiments we did a little while back using fairly simple data collected from smartphones, so making use of the quite simple sensors that are in a lot of similar consumer electronic products, like accelerometers, for example. You can access the paper on the Cambridge Service Alliance website if you've not already done so, in the resources and monthly paper downloads section. The agenda for today is quite simple. I'm going to give a brief overview and backdrop for the study, talk about why we did the study, how we did the study, a quick wrap up of the results and discussion, which are of course discussed more extensively in the white paper, then talk a little bit about future research and some other possibilities for this kind of research, and then we'll have some time at the end for questions. So as a brief overview, we're working, of course, in the space of wearable sensor technology, which we certainly think is an interesting one. This fits into a few different disciplines. The main ones are that you may have heard of are ubiquitous computing and Internet of Things. There is, of course, quite some overlap in this domain broadly with other fields. So on the technical side of things, computer science, electrical engineering, sensor fusion research, for example, and of course manufacturing. On the other side of things, psychology, organizational behavior, human resource management, among others. As far as to-market technologies, many of you are probably familiar, excuse me, with some of the wearable technology out there on the market. So we see quite commonly devices for like Fitbit, for example, for personal health and fitness monitoring, and of course functionality very similar being built now into smartwatches. And in B2B markets, there's been applications of wearable sensors in areas such as industrial safety, and of course in healthcare for monitoring health and fitness there. Another application of which is where we're working is applying these sensors, often very similar to some of the aforementioned examples, in the context of studying human resources, organizational behavior, and the dynamics and processes taking place among people in organizational settings. The reason we do this, the big one, is because it's somewhat less invasive than, for example, using methods based on human observation, videos, be that qualitative or computer vision based. It's a bit more comfortable for participants to sit there and wear a device that's mounted on a lanyard, for example, than to know that they're being video recorded. And a lot of the work we're doing builds on the quite big body of research, human activity recognition, which is itself quite broad. It spans human-computer interaction through to sports science and a few other domains along the way. And this is basically based around being able to track and identify activities performed by people based on information from sensors. So taking, for example, an accelerometer, we might have a few different axes. We have motion in the directions of these axes, and from this we're able to approximate certain actions, certain behaviors, for example, from that movement. Then from there we might say that we can use this information as a proxy or a marker for something deeper in our case. So for example, people's body language, people's interactions, being a manifestation of some sort of underlying socio-psychological process. So a bit more on the why of the study and narrowing it down a bit. As I said, the main motivation for using these kind of sensors as compared with other research tools is the relatively non-invasive nature, but it's also a very interesting research opportunity. So we know that from human activity research, human activity identification research, we can identify things like people walking up and down stairs, performing certain sports, for example. But if we take that same idea, so using fairly straightforward sensor measurements, but looking at something a bit deeper, and particularly when we also look at the interaction aspect, so interactions between people, it becomes quite an interesting research opportunity as well. So this study, as we've explained in the white paper, is very small scale, is intended just as a proof of concept kind of study, but inspired by some of the other work we've been doing, more focused on human dynamics using wearable sensors. We did a very small deployment in a financial services company following their weekly unstructured team meetings. So just members of a team, an innovation team in this company getting together and studying their behavior in these meetings. In the paper, we explain some of the variables that we get from the devices. So as I mentioned at the start, we're using the sociometric badges originally developed by MIT Media Lab. And we have included some citations in the paper there, which talks a bit more about those devices. This is a basic rundown of what we're able to get. So the devices themselves have some sensors for proximity, an accelerometer for movement, and then some microphones for audio, of course. And some of the things we get are posture with directionality, some different variables pertaining to speech, for example, and then what we're also able to do in addition to this, but wasn't so much the focus in this paper, is then also compute or derive information relating to interaction along the lines of, for example, mirroring behaviors, turn taking, and really capturing that interactivity aspect as well. These figures are from the paper, so we showed that over time we've got a few participants just plotted there in relation to each other along the lines of just two variables there. So we've got posture left and right, and posture front and back from the accelerometer in the devices. 4 participants, 1 and 2 in figure 1, and 2 and 8 in figure 2. For both in meeting 3. You can see that there's quite some movement there if we just plot that over time and look at those. And that's quite interesting, but it's perhaps more interesting and perhaps clearer if we look at it like so, when we start to represent this information as a network. So in these plots here, you've got the nodes, so the spheres representing individuals in our meeting, let's say. And then you've got lines connecting them, weighted according to the intensity of those variables. And you've got the color code there. So in this particular graph, just for illustration, we show body movement mirroring, face-to-face interaction, posture mirroring, turn taking, and volume mirroring, so with voice. And if we imagine this information collected over time, second by second, and the kind of the structural representation that we're showing here, it paints quite an interesting picture of dynamics between people and along the lines of some variables that we probably don't always think about when we're thinking about studying organizational behavior in teams. The method is fairly straightforward. We used some classifiers from the Waker machine learning library. What's maybe a bit different is we use multi-class classification, so it's not a binary classification problem, which is perhaps more common. And what's also different is we don't have a target variable as such. Instead, the targets in this classification problem are set as the individuals. So we're trying to individuate or identify the individuals, based, if you like, on the information that we saw before. So sort of creating a social behavioural signature for each of these people to be able to identify them. We've then used and reported pretty standard measures for classification, accuracy, so precision, recall, and F measure for each individual, and then overall model accuracy. In this table from the paper, we show the results from 3 classifiers. So the rep tree, basically a decision tree, the naive Bayes tree, and the random forest, so basically an ensemble decision tree. You've then got down the side meetings 1, 2, 3, and 4 that we followed for this study. Here we're showing the results of forward feature selection analysis. This works basically by adding features iteratively to the model and seeing how that influences, in our case, the overall accuracy of the model. So if you start from the bottom of the table with feature 1, we can see how much accuracy is added by just one feature alone, and then the subsequent gains or not as we add a feature. Our results showed that pretty consistently, if we look at the right-hand column for random forest, that we saw a lot of predictive power coming from 3 same features. Audio back volume, so the microphone closest to the individual wearing it, and our 2 posture variables, so posture movement left and right, and posture movement front and back. What the table also shows is where model accuracy during the forward feature selection exercise peaked. So those are highlighted in gray. So beyond this, we started to see accuracy taper off a little bit. And so one way we could look at refining the model, refining the input features, is to take that as a cutoff, for example. That's just a zoomed in version there. So that's from the random forest classifier for meeting 4. So we can see that the posture front back variable alone contributed quite a lot of predictive power. There was still quite a good improvement when we added the posture left right feature. A little bit of an improvement with audio back volume, then fairly incremental improvements thereafter, up to starting to taper off after speech profile speaking. So as I said, we got the best results from the random forest classifier, which is a good general purpose ensemble classifier, performs quite nicely, tends to fit nicely. We saw that our posture, left, right, front, back, and individual audio variables were fairly consistently the most important or powerful features across all meetings. For the final model results, we report these fully in the white paper, but we got between 67.90% overall accuracy in meeting 2, which is still okay. And for meeting 4, we got 88.20% accuracy, which is quite good. Our F measure across individuals was quite good, which is reported in the paper, and precision and recall between individuals was fairly balanced, which is another important measure we look for, particularly when we're dealing with a multi-class problem and have multiple targets. What's interesting here is that the posture variables, which we saw are quite important, capture interaction between the people. So this idea of a certain behavior signature, but also engagement with the meeting. So we saw for certain individuals, which we discuss in the paper, that there was clear signs that some people exhibited certain behaviors, which seemed to indicate whether they were more actively engaged with what was being said during the meeting, but perhaps some others who were more relaxed, and certain signs that seem to suggest that we can find unique markers for people that are in more senior positions, let's say. One of the challenges here, of course, is the fact that it is a small sample size, and also that the team composition varied between meetings. So because of the context we were looking at, the participants had the option to attend or not attend all of the meetings, just because it was following what the company does. And when you have a small sample size, this of course does create some issues, because it's difficult to make really strong comparisons and really strong assertions about how well we can identify the people involved. In the future, we would like to focus more on some a priori hypothesizing about the performance of the specific features that we look at here. Whereas in this paper, we take a very much data-driven approach. There would be the opportunity to, going forward, we will look more into informing this with theory. There's the possibility to look at more specific actions and do a more in-depth analysis of behavioral proxies for the hierarchy that's existing there in the meetings. And also looking at the impact of introducing or changing the leadership roles, both within a contrived setting, but still measuring this with the sensors, or also in natural settings. So adjusting who is a manager, for example, and who is a subordinate, or who's taking the lead on the meeting, for example. Other things we're doing going forward are looking into classifying the employees grouped under job roles. So this would be particularly interesting with and more valid with a bigger sample size. So if we had groups of junior employees, middle management, upper management, for example, and seeing if there are unique defining features there. Also looking into the identification of dyads. So within the meetings here, we have looked at identifying the individuals, but there would also be the possibility to look at identifying pairs of people, if you like, strong pairs of people, sitting somewhere between what we've done here and other research that's looked into networks in a similar way. There's also scope to do some model refinement. One possibility is to look into a bit of class balancing, for example. So this is a challenge, particularly with multi-class classification, because we want to see nice balanced results across the individuals, and not the ability to predict one individual, for example, in the group a lot better than others. As I said, definitely larger sample sizes going forward, and also potentially a comparison across different types of teams within one organization, or even indeed across different organizational settings. And finally, looking into other possibilities with different sensors and different pieces of hardware to capture similar, but get further insights on the context.